All right, hi everybody. I get a ton of questions every year in AP Statistics about z-scores, t-scores, when to use z-scores, when to use t-scores, and how many different questions are out there about normal model probability, and I don't know when to do what. So I'm going to make a quick video here to try my absolute best to explain several different situations where the normal model is used, when it can't be used, and just how do you know what to do. And those pesky conditions that are always needed when you do intervals and tests. I'm going to talk about those as we go throughout this video as well. So let's just get down to it. So there's two types of problems that you're going to encounter. Problems with proportions and problems with means. So let's first talk about proportions. So let's say that we know 15% of all jelly beans in the world are green, which means that 85% are not. So success is getting a green jelly bean. Failure is not getting a green jelly bean. So 15% versus 85%. Now, let's just say we take a completely random sample of 250 jelly beans. 250 random jelly beans taken, and we say, hey, what's the probability that more than 45 of them are green? Okay, so the moment I know that I have a sample, the moment that I am told there is a sample, I need a sampling distribution. I mean, it's in the name, sampling distribution. You need a sample because you need to understand how all samples are going to behave if you're going to understand the question that's being asked. So now, remember, there's three parts that go into creating a sampling distribution so that I can answer this question. The first is, what is the center of that sampling distribution? Well, I would certainly expect the mean of all possible sample proportions of 250 jelly beans to be, well, 15%, because that's what's true, right? Isn't 15% of jelly beans green? So wouldn't I expect, I understand some samples might be higher or lower, but I expect the mean to be 15%. And then I have the standard deviation. Oh, hold on a second, I forgot to say something. The mean is only going to be in the center as long as I'm unbiased, which means I need that sample to be random. So there's that first condition. You need the samples to be random, or else you're not going to get the mean, the true value in the center of your sampling distribution. Next comes up the standard deviation of the sampling distribution. This is going to tell me how, hey, guess what? Some samples are going to be a little bit higher than 15%. Some samples might even be a little lower than 15%. So I'm going to put 0.15, that's P, times the opposite of P, 0.85, divided by my sample size of 250. Now, as I calculate this real quick for you, what's the condition attached to this? Well, the only way standard deviation is actually allowed to be calculated is if your samples are independent of each other. So remember, sampling distribution shows you all possible sample proportions, not just one or two. It shows you all of them. And we need all those samples to be random. That's the first condition. But we also need to be independent of each other, which means what happens on one sample can't affect the next. So, to be honest, if we're sampling without replacement, that's just not true when you're sampling without replacement. Because if you take a bunch of jelly beans out, eat them all, or throw them away, when you go back to get more jelly beans, you have technically changed what's left. But the rule is the 10% condition. The 10% condition says as long as your sample size is under 10% of the population, then even if you don't replace them, you haven't taken out enough to really put a dent into the huge population. So with there being probably millions of jelly beans in the world, if I take out a random sample of 250, I'm pretty sure that I'm safe, that I'm under 10%, where yes, I'm still taking them out and not replacing them, so independence is technically violated, but any such difference because of that is negligible due to the fact that my sample is under 10% of the population. All right, so that's that second condition. All right, so my standard deviation is 0.0226. I like to round to 4 decimals. All right, next up comes, what's the shape of that sampling distribution? Well, you guessed it, normal, which is going to be awesome for us. We love the normal model. So we know that, oh, wait a minute, what's the condition? What allows the sampling distribution to be normal? Oh, yeah, every sample has to expect it to be more than 10 successes and more than 10 failures, or 10 or more successes, 10 or more failures. So I quickly have to take 250, and I expect 15% of them to be green jelly beans. That's 37.5. That number is more than 10. And then I need 250 times 85%, which is the failures, non-green jelly beans, and that number is 212.5. Both those numbers are 10 or greater, so yes, I can use a sampling distribution that's normal. All right, so now I can answer the question. See, it took me all of those things to be able to answer this question. All right, what's the probability that there are more than 45 green jelly beans? Well, 45 divided by 250 would be 18%. So essentially I'm asking the question, what's the probability that a sample proportion is greater than 18%? Well, since I'm using a normal model, then I need a z-score. Z-scores could be used in any distribution in the entire world. You don't even have to be normal to use z-scores. But if I'm going to answer this question either with a z-table based on a normal model table, or if I'm going to use normal CDF on my calculator, I need to use the z-score. So the first thing I'm going to do is find the z-score for 0.18. So I'm going to take 0.18 minus 0.15. And I'm not showing the work for this because I assume everybody knows how to find a z-score. 0.18 minus 0.15, that's the center. Hit enter, then divide that by the standard deviation, 0.0226. Now I get a z-score of 1.3333. So asking you to find a proportion greater than 18% is equivalent to asking you to find a z-score greater than 1.333 with the normal model. So you could use a z-table to get that answer, but I'm going to go ahead and grab normal CDF on my calculator. I'm going to do 1.3333, and I'm going to use the upper bound of 99. 99 is acting like infinity because I'm going to go way above. A z-score of 99 would be like unbelievably unbelievable. So don't think it'll happen. So that's acting like my infinity. And I get an answer of 0.0912. So there's about a 9% probability that I'm going to get a sample of green jelly beans that contains 45, 18% or higher, okay? And that's it. So it's pretty cool, but you know, I needed to check those conditions to make sure I could build that sampling distribution appropriately, and then I can answer the question, again, using z-scores. Proportions are always using z-scores. All right. So let's look at another problem here. Actually, it's the same problem. So we have 15% of the world's jelly beans are green, which means 85% are not. And I have a question, and this time I'm going to take a sample of 10. Okay, great. What is the probability that the sample contains more than 2? Okay, sounds a lot like the last problem. So I'm going to start going ahead and building that sampling distribution. I say, okay, what's the mean? What's the mean of all possible sample proportions out there of 10 green jelly beans? Well, 15%, as long as it's a random sample, right? Oh, and then what about the standard deviation? The standard deviation of the sampling distribution? Oh, I'm allowed to calculate this as long as my sample is under 10% of the population. Well, in the previous problem, 250 was under 10% of the population, so I'm pretty sure 10 is. So I get a standard deviation. Now notice here the standard deviation is going to be a lot bigger because smaller samples vary more. So since I'm only working with a sample size of 10, I'm going to have a lot more variance than with a sample size of 250. But now I run into a problem because I want to use the normal model. But guess what? You can't. Because with only 10 jelly beans, and I expect 15% to be green, that's only 1.5 successes. That's not big enough. So sorry, because of my sample size not being big enough, I actually cannot use a normal model to answer this question. So how can I answer this question? Well, as long as the samples are independent, as long as take a jelly bean, the probability that the next jelly bean is green or not green has no bearing on the previous, as long as I have independence between all my jelly beans, then I could actually use the binomial model. So the binomial model would say, all right, I'm looking for the probability that the number of green jelly beans, you know what, why don't I use a G there for green jelly beans? The number of green jelly beans is more than 2. All right, so to use the binomial model, you have to understand that with 10 jelly beans, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I want 2 or more of them to be green. So, I mean, only 1 of them could be green. Well, that would be bad. 0 of them could be green. That would be bad. 2 of them could be green. That'd be good. 3 good. 4 good. 5 good. Right, all the way up. So 2, 3, 4, 5. Well, actually, more than 2. So 2 would not be good. I need 3 or more. I need 3, 4, 5, 6, 7, 8, 9, or all 10 to be green. So with the binomial model, which, you know, I'm not going to reteach the entire binomial model in this video, but I'm just going to kind of walk through it. I need to find the probability that there's 3 out of 10, 4, 5, 6, 7, 8, 9, or all 10. That's actually a lot of work. I'm going to choose a little safer route here. I'm going to find the probability that there's 2, 1, and 0, because that's what I don't want. I don't want 2, 1, or 0. I want more than 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to go ahead and I'm going to find the probability that if I have 10 jelly beans, I select 0 that are green. That's 0.15 to the 0, 0.85 to the 10. 0 green, all 10 non-green. Then I'm going to take the probability of 1 green jelly bean. That's 0.15 to the first, 1 green, 0.85 to the 9, 1 green, 9 not green. And then I'm going to do 10, choose 2 for 2 green jelly beans, 0.15 squared, 2 greens, 0.85 to the 8th, 8 non-greens. Now remember, this is what I don't want. This is what I don't want. So I'm going to do 1 minus that to get the probability that it's 2 or more. Or I'm sorry, excuse me, 3 or more. Because I want, its question specifically said more than 2. More than 2. That's 3, 4, 5, 6, 7, 8, 9, 10 out of 10. So I'm going to find 0, 1, and 2. Now remember, we have a really cool shortcut in our calculator to help us with this. And it's under the same second vars where you go and get normal CDF. We're going to scroll down here boop, 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 to Binomial Cdf. Here's how Binomial Cdf works in. You type in the number of the sample size. So in our case, that's 10. So 10 green jelly, or 10 total jelly beans. And we need the probability of success. For us, getting a green jelly bean is the probability of 0.15. And the number we type in here, because we're doing a CDF, it'll do the number we type in, so 2 out of 10 or anything less, which is 1 out of 10 or 0 out of 10. So this is literally going to calculate the 3 things I want. 2 green, 1 green, or 0 green. And that is 0.82, essentially. A couple extra decimals there, but just for speed here, 0.82. But remember, that's what I don't want. So to get my final answer, I'm going to do 1 minus 0.82, which is 0.18. So it's an 18% chance that if you got 10 jelly beans, that more than 2 of them will be green. So the point of this problem is not to reteach you all the binomial model, because if you don't know the binomial model, you probably have no idea what I just did. But it's to show you that, you know, when you work with proportions and you cannot use the normal model because that third condition fails, well, then you can go ahead and use the binomial model. So that's pretty cool. All right. Now let's turn our attentions away from proportions to means. Now means work very differently, but we still can use the normal model as long as we meet the conditions. So let's check out this problem here. So let's say, and I'm honestly making this up, so please don't come at me here and tell me that I'm way wrong. I probably am way wrong, but I'm just making this up for sake of a quick problem. Let's say that of all the dolphins in the world, the average weight of a dolphin is 300 pounds. But come on, every dolphin varies a little bit, so the standard deviation of all dolphins is 250 pounds. So there's my mean, there's my standard deviation. Now, if the question says, hey, what is the probability that a dolphin is under 250 pounds? One dolphin, a dolphin. Okay, I'm trying to find the probability a dolphin is less than 250 pounds. Now, if I want to use a normal model to do this, I'm in a tough bind here. This means that, you know, I have the mean, awesome. I have the standard deviation, sweet. But I need to know that it's normal model, because a lot of kids think that z-scores, you know, only work with the normal model. No, z-scores work with anything. I mean, I could calculate the z-score right now for 250. 250 minus 300 divided by 25, right? This is simple to do. And in fact, it's a very easy number because it's divisible. It's -2, right? But I can't jump and use the normal CDF or use a normal model table if I don't know that I follow the normal model. So I would have to be told somewhere in the directions that the population of all dolphins follows a normal model. So if that is set in a problem, then like, you know, or a normal distribution, right? Or it's approximately normal. That is like amazing news, because that tells you, hey, the normal tables or the normal CDF on your calculator is fair game. So now to find the probability that a dolphin is less than 250 pounds, I need to find the probability that a z-score is less than -2. You could grab your normal model table or go and grab normal CDF on your calculator. Now I'm looking below this time, so I want to start at -infinity, which is going to be -99. I don't have an infinity button on my calculator, so I'm using -99 to be like this unbelievably low z-score, to an upper bound of -2, and I get an answer of 0.0228. 0.0228. So it's about a 2.28% chance that you're going to find a dolphin under 250 pounds. A dolphin. All right, great. Next question. Very, very similar scenario here. This time, 300 is the true mean weight of all dolphins. Standard deviation of all dolphins is 250 pounds. All right, this time, I'm not asking you about a dolphin. I'm asking you about a sample of 50 dolphins. Okay, now I got a sample. What do I do when there's a sample? Oh yeah, sampling distribution is going to be needed. Okay, so the same exact question. What's the probability that the mean of the sample, I'm not talking about a dolphin anymore, I'm talking about the mean of the sample, that's an X bar, is under 250 pounds. So I want to find the probability that a sample mean is under 250 pounds. Okay, well, if I'm going to need a sampling distribution, well, I guess I need to build the sampling distribution. All right, so let's see here. So the center of the sampling distribution is what do I expect the mean of all means to be, right? Because remember, sampling distribution doesn't just show one or two samples, it shows literally all of them. So what is the mean of all possible sample means? Well, the truth, 250, right? Whoa, I'm sorry. I'm so sorry. I was thinking the 250 from the question. I mean 300, right? Because that's the truth. If the truth is 300 pounds, then that's what should be in the center, as long as the samples are random. There's your first condition. All right, the standard deviation of the sampling distribution, well, wait a minute. This 25 is for one dolphin. One dolphin could easily be really, really small or really, really big, but I'm not talking about one dolphin. I'm talking about 50 dolphins. So the formula is to take 25 and divide it by the square root of 50, which is pretty easy. 25 divided by the square root of 50 is 3.54. We'll just use two decimals there, 3.54. All right, but remember, wait a minute, standard deviation can only be calculated if all of these samples are assumed to be independent of each other, which means that, again, I can't take out too many because then all of a sudden I run into that independence issue, or violation of independence, I should say. So again, as long as I assume that there's probably hundreds of thousands of dolphins out there, I don't know if that's true, but I bet there's a lot of them. I don't think they're endangered. So 50 is definitely under 10% of all dolphins. So there's that second condition that allows me to use the standard deviation. Now, next up is I really, really, really want that sampling distribution to be normal. Well, okay, there's a couple things going on here. First, if I know the population is normal, then any sample size is big enough and the sampling distribution will be normal. But we also have something called the central limit theorem that says, hey, guess what? As long as your sample is 30 or larger, it doesn't matter what your population works like. It does not matter. So if we go to the previous problem, when we were only looking at one dolphin, it mattered. I needed the population to follow a normal model or else I couldn't answer the question. But when I come up here, now all of a sudden I'm working with 50, I really don't need the population to be normal because the central limit theorem tells me that the sampling distribution for a mean will be normal provided that your sample size is 30 or larger. So, the end of the story here is that I'm going to be following a normal model, which is awesome, but I didn't even need the population to be normal in this scenario because my sample size is larger than 30. All right, so there's that third condition that just got checked. Well, now all I need is a z-score. So I'm going to take the question, says, hey, we're looking for 250. Actually, we're looking for less than 250. And we're going to subtract the mean of 300. We're going to divide by the standard deviation for a sample of 50, which is 3.54. Now, as I'm calculating this number, why am I using a z-score here? Because a lot of kids just say, well, if you're working with means, you got to use t. Well, here's why. You didn't study enough. You didn't learn enough. When you know the standard deviation of the population, when you know sigma, you are allowed to use z-scores, okay? 100% you are allowed to use z-scores. By the way, the z-score here is negative 14.1243. Yeah, you heard me right, negative 14, unbelievably low. So, to find the probability that a sample of 50 dolphins is less than 250, I basically need to find the probability that a z-score is less than negative 14.1243, and you probably already know the answer to this, but I'm going to find it anyway. But let me go back 1 second to what I was mentioning earlier. I'm allowed to use z-scores here because anytime you know the standard deviation of the population, z-scores are totally okay when you're working with means. All right, so it's a joke that I'm even going to calculate this, and if you know why, you know why. But I'm going to go to normal CDF. I am going to look below, so I'm going to go to negative 99. I'm going to go to a z-score of negative 14.1243, and my calculator is going to come back and say 0, because it's that unbelievably low. Like, negative 14 z-scores, like laughable. So basically the calculator is telling me, hey, this ain't gonna happen. The probability that a sample of 50 dolphins is under 250, not gonna happen. So this is actually another great kind of time where we could pause real quick. Why down here with one dolphin was it fairly likely? I mean, 2% is not unbelievably low. Why was it likely for, I wouldn't say likely, but why was it at least in the realm of possibilities that one dolphin could be under 250, where 50 dolphins, it was literally completely impossible to happen? Well, that's because bigger samples vary less. And when you're working with one dolphin, yeah, one dolphin could be kind of on the lighter side, malnourished, whatever. But a sample of 50 dolphins, it's not going to ever be that low because it's just too low. It's just, the variance is what changes. The standard deviation is what's lower. I mean, remember, for one dolphin, it's 25, but for a sample of 50, it's now 3.54. So that standard deviation really makes a big difference. All right, so now you might be wondering, well, okay, you just said that I'm allowed to use z-scores with means, but when do I need a t-score? Okay, well, that is coming. Just give me a moment. Just give me a moment. Let's do one more problem here. And this time, well, not one more. I got two more here. But this time, same thing, dolphins, right? The average weight of all dolphins is 300 pounds. And I had a question mark here, and I meant to erase that, so I'm so sorry. Let's go ahead and put a 25 there again. All right. So, 300 is the mean. Standard deviation is 25. Again, if you know this sigma, the true standard deviation, you are allowed to use z. So the only difference between this problem and the last one is I'm dealing with a sample size of 10. And I'm only bringing this up to talk to you about that central limit theorem. Because remember, the central limit theorem says, who cares what the population looks like if your sample is 30 or lower? All right. Oh my gosh, I can't believe I just said that. I'm sorry. 30 or higher. 30 or higher. You got to be big enough. So the point here is, let's review real quick. When we were only looking at one dolphin, we absolutely needed the population to be normal in order to use normal CDF or our normal model tables to get that answer. When we were working with a sample of 50, I didn't need the population to be normal because it really was okay because of the central limit theorem. So here's another question. Now, I'm not talking about one dolphin. I'm not talking about 50 dolphins. I'm talking about 10, but 10 is still not big enough. According to the central limit theorem, for a sample to be big enough, it needs to be 30 or larger. So when you're working with 10 dolphins, this is where, once again, I would absolutely need the problem to tell me that the population is normal. The mean of all samples is still going to be 300. That's what's expected. The standard deviation is now going to be 25 divided by the square root of 10, because remember, the sample size determines the standard deviation. So 25 divided by the square root of 10 is 7.91. And again, is the sampling distribution going to be normal? Well, no, unless I know the population is normal. And that's the central limit theorem. That's what I'm trying to get across to you guys here, is that if you know the population is normal, any sample size is big enough to make a sampling distribution that's normal. But if you were at 10 and the population was unknown, I'm sorry, it wouldn't work. The question would not be would not be possible. So let me just finish this off real quick. So we're going to do 250 minus 300 divided by 7.91. So 250 minus 300 divided by 7.91. That is a z-score. Still really, really low, but not quite as low in the last problem. So now to answer the question about a sample of 10 being less than 250, that's a z-score being less than negative 6.3211. So I still bet the probability is really, really, really low here, but it might not quite be giving me a 0 this time. So let's see here, negative 6.3211. And yeah, okay, listen, still really, really low. That's 9 zeros, 0.0000000001. So again, pretty darn close to 0, but not, completely, I mean, it's pretty unlikely. I'm going to joke around here. It's really low, but it's not coming back 0. All right, so what I was trying to explain to you there, hopefully, is in all three of those problems, I could use the normal model. Why? Because I knew the standard deviation of the population. I knew that, which was awesome. But, when can I use the normal model for that sampling distribution really depends on, do you know the population is normal? If so, any sample size is big enough for that sampling distribution. If it's not, or unknown, or you know it's skewed, then you definitely need that essential limit theorem. You need that sample size to be 30 or larger. All right, one more question, and yes, we are going to end here with a problem where, you better believe it, the t-model is going to be needed. All right, so in this question, a little bit different. Here, we know the mean of all dolphins is 300 pounds. Awesome, great. But we don't know the standard deviation. We have no idea what the standard deviation is. Okay, so now we're going to look at a sample of 50 dolphins, kind of similar to what we did before. And this time, we got a sample, right? So it's not like our sample's unknown. We got a sample. And the sample was 250 pounds. Okay, interesting. And the standard deviation was 36.8. Now, this is the standard deviation of our sample. Now, the question is, we're wondering, okay, cool, sample 250 pounds. All right, here's the crazy thing, right? Here's something really important. This is like one of the big ideas in statistics is if all you know is your sample, you honestly know jack squat. Because if all I know is that my sample was 250, I don't know if that's weird. I don't know if that's high. I don't know if that's low. I don't know if that's significantly high, significantly low, or just normal in the middle. I don't know until you compare it to all other samples. And to do that, you need a sampling distribution. All right, so I want to find the probability that another sample, not my sample, any other sample out there, remember there's billions of samples of 50 dolphins out there, what's the probability that any other sample is lower than mine? My mean of 250. Okay, well, once again, I need to make a sampling distribution. So the mean of the sampling distribution, as long as the samples are random, there's my first condition, is going to be 300. Why? Because that's the truth. The standard deviation for a sample of 50 is going to be, here's where I run into a snag. I'm pretending I don't know. I don't know the standard deviation of the population. What do? Well, this is where we do something really important. We're going to replace the standard deviation of the population, which we don't know, with the standard deviation of our sample. Same exact formula, just making that replacement. Well, this means I'm no longer allowed to call it the standard deviation. I have to call it standard error, the twin brother, its best friend. Same formula, but it's just replacing the population standard deviation with the standard deviation of my sample. And this, my friends, is where we now have to use a t-model. Because when you do replace the standard deviation of the population with S, the standard deviation of your sample, the normal model is just not quite accurate enough. We need one of the t-models, all depending on our degrees of freedom. So I'm still going to calculate 36.8. 36.8, trying to do it on my calculator real quick, divided by 50, and I get 5.20. Okay, but again, well, obviously, even if you're working with standard error or standard deviation, you still need that independence. So we still need our sample size to be under 10% of the population to assume independence. And then lastly, again, is now the shape, right? I really wanted to use a normal model. And, even if the central limit theorem says, hey, your sample's big enough, it's just that because I'm using this, the sample standard deviation in place of the population, that's where t is needed. So remember, t-model is just a little bit flatter, a little bit more spread out, but really not that much different in terms of what you need to know right now than the normal model. But I am going to need a t-score, so I'm going to take 250, my sample mean, and I'm trying to find the probability we're lower than that. I'm going to subtract the center, 300. I'm going to divide by the standard error, 5.20. So 250 minus 300 divided by 5.20 is negative 9.61. Negative 0.62 if we keep two decimals there. All right, so that's my t-score. I'm going to have to use a t-model here to answer this question. So to find the probability that a sample is lower than 250, I need to find the probability that a t-score is lower than negative 9.62. And to do that, I can't use normal CDF on my calculator. I'm going to have to go and grab T-CDF, which is on the same menu as normal CDF. T-CDF right there. And I'm going to, once again, I want to look lower than 250. So I'm going to start at that negative 99, which is acting like negative infinity. I'm going to go to my upper value, which is where I want to stop, negative 9.62. And now I need the degrees of freedom. And remember, degrees of freedom is just your sample size minus 1. So that'd be 49 degrees of freedom. and I'm going to go and get 0. So once again, that's really, really unlikely. So maybe I chose a bad number here. Maybe I shouldn't have chose 250 for this video because I'm not really getting some good answers here. But regardless, we still are understanding the process. So we get something that's really, really, really low, basically 0. But the point is, I needed the t-model here. Why? Because I did not know the standard deviation of the population. Now, this is what typically is going to happen when you're doing intervals or significance tests. When you're doing these things, when you're working with means, you aren't going to know this number. The only value that you are going to know is the mean of your sample and the standard deviation of your sample. And when you have to replace that S where you would normally put sigma, that's when the t-model is needed. All right? So quick video that goes over a lot of different scenarios. Sorry that my 250 was probably a poorly chosen value because a lot of the answers I'm getting here are pretty low there. Maybe I should have chosen something like 290, something that is lower than 300, but not that much lower. But regardless, I hope you understand the point. You could go back on your own and redo all these past 4 problems with 290 instead of 250 to see how you would get some more likely scenarios, but you would still get this comprehension of how to do these problems, okay? So hopefully this video might help you a little bit prior to the AP test, getting you ready. Hope it all makes sense. And if you have any questions, don't be afraid to email.